Hello everyone, and welcome back to Reverse Engineering Linux 32-bit applications. In this video, we're going to continue our discussion of malware. And in particular, we are going to look at examining sections and segments in an unknown and suspicious executable. So let's get started. So previous video, we had talked about how you could use rev037, and you could use that, for example, to look at the different sections in your program. So now I want to show you at the start of this video, at least, how you can use rev037 in order to examine some of these sections. So let's do our help again. And you'll notice that I have the option with rev037 to list out my segments, list out my sections. And I also have the ability to dump the contents of a section, either by number or by name. And I can either do a hex dump or a string dump. So let's look back here and look at a few of these sections. So I have section 2 is nodes, as is section 3. So let me go ahead and try this. So I'm going to do a hex dump on 2 and possibly 3. So I'm going to call rev037 hex dump equals 2 on Xingxi bind shell. And there you have it. That is the dump of that section as a hex dump. I can also dump it as a string. And now it just gives me the string GNU, and it doesn't give me the bytes around that. So if I wanted to do, say, section 3, I could do that as well. These are my build notes. Gives me a little bit more information about how the program was built. Some other interesting sections, I can get version information. I can get those comments. Go ahead and have a look at that. So the comments were in section 27. So this is going to tell me exactly what version of GCC was used to build this program. So that could be very useful. You know, perhaps the compiler itself had a problem too. You know, earlier when we were looking at vulnerabilities, that's something you might want to look into, but you know, this could be insightful. It's just at least interesting, at least. Okay, so what about some of these other segments? I had 25. This is my data section. And it looks like I just have some random values in here. What about 26? It says BSS has no data to dump. So this is another segment that contains some data. In this case, it doesn't though. All right, well, how about this section? So this section is a very important one. It's the text section. It's also pretty lengthy. It says here's the hex dump of the section text. Now recall that this section is used to house my program. And you might say, well, this doesn't look like a program. That's because it's not been disassembled. So how can I get this disassembled? I could use readelf. I could take these results, I could pipe them to another program, and I could try to disassemble this code. And I certainly could do that. It's just not the best way to go about it. Instead, I want to use a tool called objdump. So as always, we can do this. We can say objdump --help. And then we will get a little bit of help on how this works. It says it's able to display information from an object file. And you can tell it what you would like to see. Do you want to see the section headers? Do you want to display all the headers? So some of its functionality is very similar to readelf. Now, we are going to use this feature, disassemble. I want to disassemble all of the executable sections. I can try to disassemble everything. It's probably not a good idea, but I can do it. I can also give it some format options. One of those is -M. So I can say I want to give it certain options. I can also say, is this little endin or big endin? Those switches I don't normally need to mess with, but I am going to give it the -M, and you'll see why here in a second. So let me start by not giving it that. So I'm going to do objdump -d for disassemble on my executable. And here's why I'm going to give it the -M in an option. This defaults to the AT&T style assembly, which is probably not familiar to most people, or at least not their most common version of assembly they're going to use. Rather, most people are more familiar with the Intel version. So I'll run this again. I'll pipe it to less, and we'll talk about it a little bit. Okay, so it says this is an ELF 64-bit executable, starting with the init section. I have a function called init. What does it do? Subtracts 8 from my stack pointer, creating space on the stack. It's going to move a value to AX. It's going to do a test, and then it's going to jump based on that test. It's going to jump over this call and possibly just return. So it adds 8 back to the stack, restoring it to its previous place, and then it returns. Now, a couple of things. this is going to give me all of those symbols. Remember, we used NM a couple videos back in order to list all of the symbols. Because I haven't stripped this executable, all of these different functions are labeled, if you will. And hopefully they have decent names, which will try to help me gain an understanding of what is going on with this particular executable. I have my PLT section. Recall that this section is used for these lookup tables. So here I have put char. I have put char here. Set sock opt right. Get process ID. F close. Stir length. Stack check fail. System. So look at all these. All I'm doing is I'm going to jump to a certain location. I'm going to push 6 on my stack, and I'm going to jump. And these all have the same format. Push value, jump, etc. So I can look at this section, and once again I can see what functions are being used, what functions are being imported. htons, dupe2, send, memset, close, read, libc start main, fgets, strcomp, fprintf, malloc, fflush, listen, bind, popen, fopen, b0, accept, exit, fwrite, fork, stir, socket, and that's pretty much it for that section. So I'm able to see what sort of things are being done in this executable. Now, I wouldn't have the nice convenient names, but even if I strip the symbols, I will have these names. I will be able to tell what library functions are being called. Just because I strip an executable doesn't mean that I don't still have to have the names of these library functions, because they have to be found. And here I have my text section. This is my program. It begins with a start. You might recall from before, we saw this when we were looking at disassembly. I'm going to zero out BP with XOR. I'm going to move some values around, and here you'll see that I'm going to call to this location libc start main PLT, and then I have some other functions. Because I didn't strip the binary, I have nice function names. Even if I did, I would still have access to all of these library functions. I would still be able to tell which one of those were being called. So register TM clones, do global detours aux. You might say, what does that do? That one is not so straightforward. Frame dummy and malloc. If I look inside this function, I will see calls to malloc and also to memset. see a function called daemonize. If I didn't have the name, it might be a little harder to figure out what's happening, although I notice there's a call to fork and also a call to exit right here. Write process ID to file. Again, I'm getting a process ID, opening a file, using fprintf, and closing a file. So I can tell that I'm getting process information and that I'm also writing things out to disk. Log file, opens the file, uses fprintf again, closes the file. The main function, what does it do? It's going to allocate some memory. It's going to use putchar, popen, fgets, stir, so I'm doing some string comparison. Calling daemonize, calling write PID to file, using fwrite, logging, fwrite again, creating a socket, writing some more stuff out, using htons, so this is used again to convert IP addresses, zeroing something out, setting my socket options, calling fwrite, calling bind. I'm going to listen on a socket. Before I can do that, I have to bind the socket. Once again, I'm outputting to a file, calling exit. Here I'm calling listen. So I bound the socket. Now I'm going to listen on it. Writing stuff to a file. Call exit, calling fflush. Here I'm checking the string length of something, writing something, reading, using stir compare again, stir, and this kind of goes on and on. You can get the idea that it's not really all that much work to trace through this function. And we haven't really talked a lot about the assembly here. We just kind of traced through it by kind of reading the comments, if you will. It's not quite what we're doing, but we're just looking at what sort of things are getting called here. And we're using that as our basis. We have another section. This one's not as important. And a couple of other little sections as well. So that is the basics of using objdump. Now, something I definitely should mention. Objdump will do a static analysis. What does that mean? It's going to look at that file and say, it looks like this is the code section. This is what I think the code section is. Now, if I put in the middle of my code a whole bunch of data, that could mess up objdump. So for example, if you look at a file system, let's say it's a FAT file system, it could be NTFS. And if you look at the volume boot record, that set of code that is in the very first sector of that partition, you'll notice there are 3 bytes for an instruction. That instruction is typically a short jump that jumps over a bunch of parameters that are stored right after that. And then the assembly code picks up, say 50 bytes later or so. Those kinds of things could possibly confuse objdump. So there are some times where you might run objdump and it doesn't correctly disassemble a file for that reason. Other reasons, it might not correctly disassemble a file. Maybe someone is trying to do some obfuscation. Maybe they have something fancy like self-modifying code. Now recall that that's a little bit hard to do with Linux, at least, because with Linux, I'm going to have my different sections and they all have different permissions. So here I have executable areas, but I don't have writable and executable areas. So I'm not saying you can't create self-modifying code. I'm just going to say that it's rather complicated to try to do something like that in a modern version of Linux. Not impossible, but not easy. There are some other issues you might run into. Maybe the code is just a little bit strange. Again, if you do things like store data in the middle of your code, it can cause some troubles as well. So if someone has gone out of their way to try to make it difficult for you to analyze their file, then objdump might be somewhat limited, and you might actually have to load it up in a debugger and do some things that we'll talk about later in this course. So that is our introduction to seeing sections and segments using a tool like readelf, and then if it's code, we can use a tool like objdump. And that brings us to the close of this particular video. Just as a reminder, this video is one in a family of videos that we have here at Pentester Academy, your source for all things InfoSec. And I look forward to seeing you in this course or another course soon. See you then.